Should be about now.
It should be about now, by golly. We are ready. The talking heads are us, and doggone if it's not episode number 133. It's over 2.5 years of every Monday. Your SBAU Astro Hour, hosted by me and accompanied by my good friends who are all more intelligent than me, but that's the whole reason I guess I'm the MC. I'm learning. It's for September 4th through the 10th, everybody, getting in the fall 2023. Our longtime South Coast Telescope and Astrophysics Club, the Santa Barbara Astronomical Unit, has served our beautiful community for about half a century, mostly out at the Santa Barbara Museum of Natural History. Our support benefactor, some board members and movers and shakers going to join our support benefactor group here in a minute. I'm the vice president of the club proudly. We're going to have elections in about 3 months. Every Monday morning, we gather together on Zoom, and you can see us 20 seconds later on YouTube. And Tim Crawford is not watching YouTube today. He's actually joining us. I'll introduce you to him. And there's a new lady named Mary who may be watching us. And there's a nice little group of people that enjoy the Astro Hour. Let's talk about Sir Isaac Newton, part of the potpourri of President Jerry's talking points. Isaac Newton's laws of motion. There's mainly 3 of them. We're going to get into it this hour and how they apply today versus in the old days. We're going to check on the planets. Venus, I guess, is out of retrograde. Mercury is down there. Jupiter took a hit. I'm not sure if it can handle any more of those damn incoming asteroids, but that's what happened. Update what's on the surface of the moon, 4th quarter, passing near Uranus, and the asteroid 8 Flora is back in the news with Helix Nebula. It's close by. Sporting Mars. You know what? We don't ever look at Mars's moons, do we? There's not much to them, but Saturn and their moon's going to come up. Let's meet the gang and then have the silly cartoons from President Jerry Wilson. Hello, Jer. Good morning again.
Good morning.
Missed you Friday night, but it was non-life threatening and it was not COVID or RSV and getting over it, whatever it is. Not very painful.
Happy Labor Day.
Yeah, it is. Happy Labor Day, everybody. Yeah. 6, 7 years we've been in office with us as our beloved.
Something like that.
Something like that.
2017 was my first office.
Well, that's 6. President. And I joined about 2 years after you when the young man went down to Caltech and dropped out of vice president's position. He was booking things. Adrian, is that his name?
Adrian, yeah.
Yeah, I guess he went into mathematics. Just thinking about having him come do a talk for us, but you want to hear math for an hour? I don't know.
It's exciting.
Yeah, let's meet the rest of the gang here. Joining us, Tom Whittemore, wife Maureen. Incidentally, Jerry's married to Pat Forgey, taking good care of her husband. And how's Maureen, Tom?
Fine, she's still fine. Yeah.
Well, bless your heart. You missed a good show on Friday night, but as a retired Westmont College science instructor, you got a pretty comfortable life. You edit our newsletter and you set your telescope up at night outside, like a lot of them. This man does a lot of it. Bruce Murdoch, who's married to Bonnie, was there at the Friday meeting and had a great show at the beginning. And we'll talk to you in a few minutes about what you've been doing with your telescope. You got several or just one big one, Bruce?
For me?
Bruce, yeah.
I have, I think, 4 telescopes. I got an 11-inch, an 8-inch, a 5-inch, a 4-inch.
Get another. Yeah, they're having a sale this weekend at Target. How many do you have, Tim Crawford?
I got 3.
Do you really? How many have you guys made? You probably have because you run the Tuesday workshop show, don't you, on Zoom?
No, Jerry and Tom Totten do, but no, I used to. But I have two of my 3 are handcrafted.
Okay, we're gonna have to do a Monday morning sometime. A big part of it on making telescopes, or what's going on.
Sounds like a good idea.
However, we got some silly stuff to get us in the mood for a laid back, closed down. Even my pharmacy was closed down this morning. I walked down to Ralph's to get something and they just wouldn't open at 9. So happy Labor Day to them. They're not laboring. We got silly stuff. These are the science cartoons that gets forwarded to all of us from President Jerry. I assume if you wanted these sent to you, and he might be amenable to it, right? Some of the new members. We had a good crowd.
I've shown ones that people suggest.
All right, let's see what's on the screen to get us in a light mood here. Oh my God.
Yeah, I like this one.
Vast check of the dinosaurs. Did they really rule the earth? Nope. False. It's never been proven that dinosaurs had administrative skills. Their administration just didn't pull it. So they got
Uh-huh.
voted out. I like this one. You give a man a fish and you'll feed him for a day. The old saying, I think it might be biblical in origin. If you teach him to fish, you'll feed him for a lifetime. No. Teach a man to embrace the paradoxes of quantum mechanics, and this man will give himself the same fish over and over again in an eternal loop of temporal torment. There's something to that. Okay. Frank and Ernest are chattering back and forth about, I just loved gravity. I discovered it. On the other side, the other guy says, I just discovered Jerry's levity, sending us these cartoons. And here is what really happened, despite Kubrick's monolith. The ancient rock was piling. I guess that's what they were hurting him. Oh, they're turning him on to fire, maybe, but not ready for pyramids. Let's come back in a million years. These are the aliens, and it's not a big black slab at all. We are here in the Milky Way. You're missing
I like this one.
are over here. If you've ever wondered,
I didn't see that one.
can you enlarge that just a bit there? And here we go. The professor makes the horrifying discovery that messages sent across the universe by advanced alien civilizations in unknown solar systems have all been going into her junk mail folder. Tessa Flanagan, she likes to share those with us. Our future secretary needs a little larger. This would be which one is this one again? It's not Calvin and Hobbes.
Yeah,
BC.
What, it's two H. All right, it's two prehistoric cavemen.
Yeah, right.
Guy says, "What's up?" Oh, I call it a telescope. Really? It brings the stars into better view. Well, let me try it. Sure enough, by golly, it works when I stand on the damn thing. Took Galileo to teach him how to do it right. Here's Dilbert. Is that the boss talking to the guy? Is that Dilbert?
Oh, yeah.
Yeah, the pointy-haired boss.
Okay.
Wally is a do nothing.
Asking, how's your quantum computer prototype coming along? Huh? Great, he says. Project exists in a simultaneous state of being both totally successful and not even started. Boss says, well, can I observe it? Well, that's kind of a tricky question. Definitely a joke for people that understand quantum. There we go. Good set of cartoons this month. Appreciate it, Jerry. You missed a good show Friday, but I'm glad you were taken care of. And next month we get Bob Berman talking in Farrant Hall. We're going to be moved back down to the little 80-seat hall, and he's the. You ever read his column? Anybody read Bob Berman's column?
Oh, yeah.
Okay, he's well known then.
Yeah.
And he normally gets paid a lot more than we're paying him, but he said, yeah, I'd like to do your party. What are we? Oh, here we go. We're going to talk about Isaac Newton's laws of motion.
Well, we're going to talk about, what I prepared is
This is light.
a talk. This is Einstein, or not Einstein. Isaac Newton did a lot of good stuff, was truly a genius. Here he's discovering the dispersion of light, breaking it up into different colors with prisms. But we're not going to get down into the bushes and trees. We're just going to look at the forest for Isaac Newton. And you'll see the method to my madness. Isaac did a lot of things that include, he was, for example, Lord of the Exchequer in England, which means he was the treasurer. So he had a lot of money. He came from a wealthy family. He had his own country estate, which he retreated to in the 1660s because of a plague outbreak in London. And he stayed pretty much by himself. I believe he was a germaphobe. And that's when he did a lot of his writing, was in solitude in the country. And so his stuff dates from the mid 1600s. He developed differential and integral calculus along with the German Leibniz. They're given co-credit for discovering it in parallel at the same time, but each of them claim that the other one is an idiot and that they really developed themselves.
Do you understand all that? Do you know the difference between differential and integral calculus? I had no idea there's
Yes,
two.
differential is, these are very easy to explain, but I need a couple of quick graphics. Differential is breaking things up into small pieces and figuring out, for example, the slope of a curve. It's the difference.
Oh, the area under two. Oh, that's the integral. Never mind.
Yeah, this is integral. This is the difference between two functions. So it gets into a higher form of math, but it's very simple in concept. The integral calculus is, for example, if you take a square and you know the area of the square is equal to height times width. So
Okay.
you want to know the area under a certain curve. You break it up into a tall rectangle that goes from the axis origin up to your curve. And then the calculus part is that you take the limit where the size of that square goes down to very, very small, not to nothing, but to very, very small things. And you add up. It's a technique for adding up all the areas of all those little rectangles. So you can break down any curve into a group of rectangles and then simply add them up to get the area under it. Sounds easy, but it can give you nightmares on homework.
Well, my vague recollection of what it's described as changing factors, changing speeds. The whole math is like flying into orbit. Things
basically, you have position, and the change of position with time, that's a differential, which is velocity. And then there's changing velocity with unit time, that's an acceleration, and that's a differential also.
You suppose he invented the slide rule?
Slide rule?
Yeah,
That's a good question. I don't know who developed the slide rule. It's quite a useful thing. It's like a Western, like an abacus for Western civilization.
In other words, it's been replaced by computers these days, I'm sure.
No, computers just, yes, they do, but computers just do it faster.
Oh, okay.
So he proposed the three laws of motion. He proposed the law of universal gravitation. He discovered light dispersion, which was in that picture we just saw, and he invented the reflecting telescope.
Really?
Quite a number of achievements.
He was the guy that came up and decided no more lenses, or at least use the lens in the front, but in the back, it's going to be a concave, not convex.
Yeah, that's why we call them Newtonian telescopes.
I didn't know that. I'll be darned.
So Newtonian mechanics, the three laws of motion, are the basis of our modern space program. We rely on this to get objects into orbit, to get them to the moon accurately, and to aim at Mars, and 8 months later hit the target right on. His three laws of motion and the law of gravitation, these are the three laws. An object will not change its motion unless force is acted on it. So if you have a rock in space moving along, it's not going to change its speed or velocity at all unless it's acted on by an external force. And the famous phrase from Star Trek, now this is in a Scottish accent, Captain, I didn't know how long I can maintain this speed. That's completely wrong, because once you get the starship going, you shut the engines off and it will continue to go at the same speed without any additional energy being added to it. So that it's not like a car where you have to keep your foot on the gas. You do that because you're overcoming wind resistance and you're overcoming friction. But in space, there's none of that. Pardon?
And the force of gravity when you're going up a hill.
Yes.
Until you wrote that, Jerry, I would have never thought of that. But when you just said that's a fiction there, that was really, I don't know how many times I heard Scotty say that. It never occurred to me.
Yeah.
By the way, the slide rule was invented in 1815.
Oh, well, that's
the what? Oh, the slide rule? Okay.
Was invented in 1815.
I thought he came later than that.
Well, Peter,
Newton was 1660.
Log slide rule.
Oh,
The slide rule is an adding machine, but it adds logarithms,
I'll be damned.
which is equivalent to multiplication and division, adding and subtracting.
It's an analog computer.
Right.
So his second law, the force on an object is equal to its mass times its acceleration. That's F equals ma, and that we use that in orbits along with the gravitational law. And then we have when two objects interact, they have mass, they apply a force to each other of equal magnitude and opposite direction. This is what we use in rockets. Excuse me, I started to talk about gravitation with two masses. When two objects interact, if you push one away, for every action, there's an equal and opposite reaction. We use that in rockets. We throw mass out the back of the rocket at very high velocity, and that propels the rocket the other way. So,
well, if it had
There's
a wall,
also-
if
There's
it had
also a pressure component to that.
what?
The rocketry, in addition to the mass of the gas that's going to the back, there's a pressure component pushing on the rocket nozzle. So the shape of the rocket nozzle very much affects how much thrust you can get out of the
The
rocket.
shape of the rocket nozzle is to increase the velocity of the outflow through the Bernoulli effect.
Right, but as it expands, if
Right.
if the nozzle itself, the throat, there you're talking about Bernoulli, but then if you didn't have anything past that, you just let it expand, you would lose all that energy. But the rocket nozzle gracefully expands it and extracts a push from it. Pressure.
Right, hydrostatic pressure, and I guess it's not static, is it?
Well,
So anyway, these laws define our space program today. There's no need for more advanced stuff. The only thing in our common everyday life that we use that depends on Einstein is GPS system. You have to do a general relativity correction, otherwise you couldn't get more accurate than several hundred feet.
really? It comes
Yes.
from Einstein's relativity theory?
Yeah.
Right.
Now, this is Newton's law of gravitation, which he also did. He was very prolific. You have two masses. These could be a dust mote and a slightly smaller dust mote in space, and they will attract each other with a force. Anything that has mass has a gravitational force between it. The gravitational force, it turns out, is the weakest force in our universe that we know of. It's 10 to the 40 times weaker than the electromagnetic force. If this were a proton and an electron, they would attract each other, but it would be through electrostatics, which is a much stronger force. But if they're neutrally charged, then gravity is what brings them together. And this eventually forms larger masses in space and stars and planets. And it's proportional to the mass, the two masses multiplied together, divided by the square of the distance between them, times a universal gravitational constant called G. This is not the same G as the G force when you are in an airplane and you can feel that motion up and down. That's little g, and that's a quantity that's unique to the Earth's atmosphere. This is the universal constant of gravitation.
Now the capital F means gravity in that
Force.
force.
Yeah, force. And
G
they're
is
pulling,
gravity. Okay.
yeah, and the force on the two objects pulls them together. They experience the same force. So F1 equals F2
Equals the gravity times.
And this is his telescope. This is a very small telescope. I think this is a 2-inch or 2.5-inch primary. And they would make eyepieces, real small eyepieces at the time, by dripping glass into water, and it would freeze into a small sphere. And then they'd pick the one that had a real small focal length that they could squint through and see an image.
Huh.
Well,
Where you got that image? This was Wikipedia.
What's that?
I see where you got the image of the force between two masses from
All right,
Wikipedia.
Yes, that is correct.
Can you put it back on that telescope, Jer? Just for
Yeah.
a second. The light comes in on the left. That's the lens.
Yeah, comes
Pointed
down
up.
this way.
And there's a mirror down at the bottom of the right, but he's
Right.
looking into it up on the left, right?
Yeah, right there.
Right,
And
there's a
it's-
diagonal mirror in there that intercepts the focused light.
And it's in the
Takes it out
center
the
of the
side.
whole incoming
Yep.
light.
Yep.
And it goes around it and hits the back end and focuses. Okay.
You got it.
He's the first one to do that, huh?
Yes.
Pretty much how telescopes are today, isn't it?
So
Yeah.
what Einstein did, not Einstein, what Newton did was he observed things that were in the common, everybody had experience with. If you're walking through a crowd and someone runs into you and you bounce off each other momentarily, that's a force. You know what what Newton is talking about when he talks about forces. These are things that humans can relate to because they're on the scale of human experience. So his stuff was a quantification of sort of obvious empiricism. He looked around, quantified it, measured it, and then he formulated those rules for it. And that is very intuitive. But that science after him came developed outside of the human scale. And that's why the universe appears to be counterintuitive, because we don't run into the things that science now describes. We don't run into them in our everyday lives. So the outside the human scale is going to very, very massive objects. And Einstein's, Newton's law do not apply to that. He did it for laboratory size things. Very high speeds. He was talking about horse carts and stuff and cannonballs and stuff. So and he did not know there was a limit to the speeds in the universe. There was no speed of light discussion. And to very small systems. That is, he was taking very small things like lenses for the eyepiece of that telescope, which is about 1 millimeter in diameter. But here we got interested in things on the scale of the atom. Now, we don't normally view that stuff in everyday life. So when the descriptions started coming out, deductively derived using mathematics from observations, experimental observation, as instruments improved and got more accurate and more sensitive, we started developing things, rules and laws that applied outside of the human scale. And that's where we start getting into the universe being counterintuitive. You can eventually develop an intuition for it after you study the math, but it comes out of the math how the universe works. So,
can I ask a question?
Yes, please.
Does centrifugal force fall into any one of those three? I mean, if Isaac saw the apple fall from the tree and said, "That doggone it, that's gravity," you suppose he never saw the old bucket full of water being twirled around and not falling out on him?
He might have. Now that's a reference frame force. It just depends on what reference frame you're in, whether you see that force or not. It's not a fundamental force of nature.
Centripetal is.
Well, it's going to give us our artificial gravity when we go to different planets.
Yeah, it's very useful. As long as you're rotating around a central core, then you'll get that. And I think that you're going to see when they start building hotels in space, which I guess someone like Hilton or something was planning on it for about 2 years from now. When they start doing that, you're going to see these big things rotating. So
something I heard about the 2001 movie is that the uncompleted 2-level turning space station that Dr. Floyd lands in the movie, it's turning too damn fast. We can see it just slowly turning, but even that's too fast at that large, I guess. I don't know my mechanics on that, but should barely turn and you'll be fine to get a 1G.
Yeah.
Well, that's all a personification of the second law of Newton, because you're changing the direction it's going. That takes a force. If it goes in pain.
Yeah, because you're not moving in a straight line inside that rotating sphere. You're moving in a curve. And in order to move a curve, you have to have a force applied to you.
Well, does it occur to you that in the world of spinning inside that kind of, the fake gravity, it takes a concave surface, but in the world of gravity, it takes convex? Do you know what I'm talking about?
Vaguely. I think I get the idea.
Any planet we're on, anything that has gravity is curved around and we're on it. But if we're inside,
we don't feel the centripetal or centrifugal force of the Earth's rotation. Right now, we're each doing about 600 miles an hour toward the east. And but that's not enough to cause us to fly off the planet. Gravity is far stronger than any centrifugal or centripetal force that we're feeling.
Yeah. Well, I was just saying the surfaces that are required to pull it
Yeah.
off. You have to have concave for centrifugal, and for
You have to
gravity.
have something. Weight is the resistance to your motion, and you have to have something to keep you from flying in the straight line that Newton's second or first law says that you want to be in, and that's the floor continually coming up at you. So you have to be on an inside surface. If you're on an outside surface, you'd fly off into space.
Yeah, right.
So anyway, the next major steps in physics were into realms that our senses cannot readily observe. In the mid 1800s, this was the topics of the day were classical thermodynamics and classical electricity and magnetism. These were formulated in 1865 by the famous Maxwell equations, 4 equations that really showed that electricity and magnetism were 2 sides of the same coin. In the 20th century, right at the beginning, the worlds of atoms were formalized in the form of quantum mechanics, and new gravity for higher masses was presented by Einstein's relativity. So relativity came first. Around the same time, they were both developed, actually. Einstein's relativity hit in 2017, and there was not much left to do except try and solve his equations. The quantum mechanics was developed, the interpretation of it was developed from the teens up to present days. They used to say only 3 people on Earth really understood, quantum mechanics? But today I've heard it that nobody understands quantum mechanics. So,
Hey, Jerry, can I ask a question about the quantum mechanics? I know that light had it was seen as a particle, and then it was seen as a wave as well.
yeah, that's called the wave particle duality. That's not.
That is not quantum.
That is quantum. It is a property of the quantum world. There are 2 types of quantum mechanics. Not in their math formalisms. There's many types of quantum mechanics in that. Matrix mechanics or the Schrodinger equation, for example, are 2. But the first thing that was quantized was angular momentum. Angular momentum comes in little chunks. It's not smooth. And that's how, when you get orbitals around atoms, the angular momentum comes in little chunks, certain layers of electron clouds. The other quantization is called second quantization, and it's a quantization of the particle field, that is, and it relies on the creation and annihilation operators.
It's a nice way of thinking about the quantization in the atoms. For example, there's only certain layers that the electrons can exist, because if you look at the electron as a wave, the orbit that it has to be an integral number of wavelengths.
Huh.
Otherwise, it cancels itself out.
Right.
Would those wavelengths be on the electromagnetic spectrum somewhere?
Yes.
No, those are not
exactly.
electromagnetic waves. Those are matter waves.
Yeah.
Right.
I mean, they're not between gammas and X-rays or radio or vision or anything.
Well,
They're just...
E equals h nu, or h is Planck's constant. Nu is the frequency, and so the wavelength is the reciprocal of the frequency. So you if you know the energy E, divide by Planck's constant, and you get the frequency at which that wave, that particle is, and that frequency in a circular orbit has to be an integral number of wavelengths. If it isn't, it decays to an orbit that it does achieve.
But the difference, as Bruce is pointing out, the difference between 2 energy levels, that is the energy that will show up as a photon if that's an transition to make a photon. So anyway, this brings us down to the great quantum quandary of today, and that is that we have 2 modern physics things that are absolutely true. That is, quantum mechanics is true. It has failed no experiments. Einstein's general relativity is true. It has failed no experiments. And the two do not include each other. So they are separate laws. How to get them together into a unified field theory is a major unsolved problem.
Well, they're coming up with some major computers, man, that are going to be just instant. Yeah, as we had one speaker talk, they're doing it out at UCSB. They're making quantum computers that use atoms somehow instead of bytes or zeros.
You're talking about quantum computers,
yeah,
qubits.
right. You're using the quantum.
That's a field that I don't understand, so I'm not going to discuss that. So.
Would it be fair to say that the quantum world involves the force of electromagnetism and really gravity doesn't play, you don't have an electron being gravitationally attracted to a proton. It's all electrical, isn't it? There's very little gravity down there.
No, there are four forces, recognized four forces.
Yeah, there's two others that existed.
Strong force, the electromagnetic force, and the gravitational force. Inside of atoms, it's the world of the strong and weak interaction inside the nucleus. In the atom, it's electromagnetic forces. And on our scale, the strongest force is electromagnetic. When you push your finger against the wall, your electromagnetic field of your atoms is pushing against the electromagnetic field of the wall's atoms. So it's force field against force field. And then the gravitation is on the larger scale.
Wow.
And old man Newton didn't know much of this, did he, at the time? Knew none of it, I guess.
He would have done very well if he'd have had the instruments to generate data that couldn't be explained. So he was a problem solver.
He was the exchequer, the Colin Taylor of England. That's interesting.
So that was a discussion of why the world is so counterintuitive. The world of modern science is.
Yeah. Outside the human scale. Fascinating stuff. It really is. We could talk about it all day. However, we got some other things. Venus just ended their retrograde, or do you want to go to the moon?
Wherever you like.
Well, whatever's next on your, I'll tie right into whatever's on your scrolling.
Yeah, Venus has become the morning star.
Again, retrograde.
And this is looking east from a low horizon. It's not Santa Barbara, probably, unless you're up on the hill where Tom lives. And this is 6 a.m. on the 5th, which is tomorrow. And here we have Venus. I have a lot of stuff up at that time. But here is Venus rising. It's next to M67. And the major thing up here for naked eye is the beehive cluster. We showed that a little bit last time. It's a very bright cluster, has a lot of dramatic stars in it. You need a wide field to really capture it.
Yeah.
A lot of red giants there. A lot of blue-white hot stars.
A beehive.
The beehive.
The word I never saw before. I assume it's opposite. It's prograde, where Venus is now headed in the same direction we are, right?
No, it's headed in the same direction that it's headed in
its orbit.
It's an apparent motion from the Earth. It's a combination of the two motions. When you drive down the street and you pass a slightly slower car, that car is in retrograde compared to you because it appears to be moving behind you.
You've had that experience probably parking at certain times when the car next to you starts to back out and all of a sudden you're going fast. You put the brakes on and nothing happens.
Yeah, I've done that a number of times.
Yeah, I know, but I mean, it's the same. That's the principle you're talking about.
That's exactly right.
Well, if the planet is coming from behind the sun, it's going one direction. Once it gets around to go in our direction on our side of the sun, it changes. That's the two, isn't it?
It's moving. It just moved into the morning sky. So that's going this way. And now, not due to the rotation of the Earth, but it's now going to start getting closer to the sun.
Okay,
is that right, Tom?
Turn the corner. Right. I got it. Prograde. That's a new word for the day. Gotcha.
Yeah, it means going forward.
Fascinating.
So this is a preview of what's coming up in the next season, the spring season. Let's see, where am I with that? Let's see, no other stars, like no other planets up there, I guess. We do have Juno, the asteroid Juno here.
There's some constellations in there, I'm sure.
Oh, yeah.
Here we go to the big moon. Oh, is this the moon or Mercury? This
This is the moon.
this is the moon. All right.
The stuff on Mercury, the craters look different. And the craters on Pluto look different yet.
Really?
So these are our standard craters. This is a picture of the full moon down here. But now we've got a terminator because we're about 3 days past full. No, full was last Wednesday.
Yeah.
And the last quarter where it's straight down, that's going to be this Wednesday. So
Right.
along the terminator's probably along here, it might be a little past Hercules and Atlas by today. But these are very dramatic craters and good views. You can see the contrast you get with crater rim lit, and here this is lit, and this crater is in shadow because it's about going, this is sunset on that crater.
Is Serenity Michael Jordan's head in this picture, Jerry?
Is what?
Is the Sea of Serenity, is that the pic? You know how I always say that Michael Jordan is the all the seas on the right there, so his head would be where the box is.
It's supposed to look like Michael
I've never
Jordan's
heard the
head.
Michael Jordan thing.
Oh, you haven't? Oh, well, where the
Uh-uh.
box is, that's the head of a basketball player, and below it is his body, legs, and off to the right, I think it's Chrysium is the basketball.
Oh, this one, Mark Risium.
Yeah, that's
I think that's stretching a little bit, Tom. When certain things are pointed out to me, like the man in the moon or the different things on the moon, the rabbit on the moon, then I can't unsee them. But Michael Jordan, I can unsee. I don't see it.
They call his shoes Air Jordans, but there's no air on the moon. I'm sorry,
So
Tim.
there's no idea.
But these are the two
Actually,
muscle men of myth, aren't they? Suppose they were discovered.
Technically, the moon, as of 1969, the moon technically has an atmosphere. And the atmosphere is made up of rocket exhaust. It's there, it's measurable, but don't depend on it for weather.
Well, remember Hosea Menace when he asked, if you get to Mars, you think there's life on Mars? He says, well, maybe if I land on a Saturday night.
Yeah, right.
I never heard that.
This is a very prominent crater. It is up. Let's see. Clavius is right there.
Oh, 2001's Clavius.
Yeah, but you'll see it well on this Wednesday, even up till then. This is a very high resolution picture taken from the Lunar Reconnaissance Orbiter camera, LROC. And it's got it's a very old crater, and you can tell that because all the craters that are on top of it.
Yep.
If this were the more recent crater, then it would have washed out all these other craters. So of these other craters hit later, it did fill up with lava. It has a lava lake in it that hardened when the crater was formed. And so it's very old. The distinctive pattern, it's the second biggest crater on the moon. The distinctive pattern is this arc of 5, or depending on this one, 6, but 5 craters in a slight arc of decreasing size. That's distinctive. No other crater has that. This is also the crater where Stanley Kubrick tells us there is a monolith buried.
Yep. And the reason they look different from Mars and Mercury's craters is that somehow Mars and Mercury have erosion.
No.
Not erosion.
No,
well, they had it on Mars, did they?
Yeah, they do have they did have erosion on Mars, but that's not
They still do. I mean, they have an atmosphere and they get dust storms.
Yeah.
But why are they different on Mercury, I wonder?
It's the material it's made out of.
Oh,
they when they hit. This one tends to have a surface that turns to lava or liquid and then hardens over, leaving these smooth surfaces. Or it produces these central peaks, which is where that liquid, when something hits with tremendous kinetic energy, I mean, these objects are hitting at up to 70,000 miles an hour, mostly in the 30,000 mile an hour range. And it weighs, it's about a mile across, or in this case, several miles across. That's a lot of energy. The energy is 1/2 mass times velocity squared. So that energy is released as heat, and it throws a lot of particles out, but it also liquefies both the incoming object and the moon's surface that it hit. For a while, it turns to a liquid, and then it very rapidly freezes. And when it rebounds in the middle, like a water droplet will do when it hits water, and then it starts coming back up again, and then it freezes, that's where you get these central peaks. So when I was a kid, we were told that's the object that hit, and it's just stuck this far in the surface, but that's not the case. There's too much energy. The hitting body does not survive as a solid object. So it basically is like you take watery mud and you throw it into some mud, and it makes a crater in a pie pan in your backyard, which I used to do. That's what you get.
well,
I can see you doing that.
For
Well,
you,
go ahead.
for you longtime telescope freaks, is it your understanding that we've never seen a rock, whatever asteroid, I guess, hit the moon ever? Has that
No.
ever been recorded in the history of telescopes?
Nope, we've seen a lot of them hit. There was one a few months or a few years ago or something that was quite noticeable. People are taking videos of the moon, because when you take videos of the moon, it's made up of a large number of still frames. And then you have a program like Registax that picks out, you say you have 10,000 images of the moon, and you go through and you pick out the best out of the 10,000, and then you stack them. And you get incredible resolution for amateur telescopes, unless the sky was so wiggly in the air that it really screwed your image up. But when they take these videos to get a better moon photo, sometimes they see all of a sudden a bright flash.
Really?
And so a lot of these things are captured that way. And then the orbiter like this one, the Lunar Reconnaissance Orbiter, which I think is still up there, it'll go over and they'll examine the moon and they'll find the new crater where it was. Mostly they're small things that hit.
Thank God.
The Lunar Orbiter just found the crashed Russian lunar probe that hit when it was trying to go into orbit around the moon.
Oh, really?
So
I
they
didn't know
spotted
that.
the crater where it hit.
The one recently, a couple of weeks ago?
Yeah, a couple of weeks ago.
It's on the South Pole, isn't it?
I forget. I don't think it was trying to land. I think it was trying to enter orbit.
Really?
But don't quote me on that. Yeah. And I don't know exactly where it is, but I saw a picture where the LRO got it as it flew over. The first thing that there was a Air Force satellite called Clementine back in the early 80s, I think, maybe early 90s. And that was a Air Force contract. It was an Air Force satellite for reconnaissance of the moon. And that was the first spacecraft to detect water on the south pole of the moon. They got a radar return from hydrogen.
In other words, there may be water elsewhere, but it's buried away from the sunlight, but it could be open, just dark on the South Pole because the sun never shines on it, right?
South Pole is the ideal situation for colonization or building a lunar base like we build in Antarctica. The craters there, the bottom of the crater is in perpetual darkness. So the heat of the sun never gets there. And there apparently is ice of some form on there, water ice in the craters, large quantities of it. But up on the rim of the crater, you're in perpetual sunlight. The sun never sets. So you can put your solar panels up there, and you can have your dormitory around there, and you don't have to endure 2 weeks of darkness like you would anywhere else on the moon. So the target for everybody is the South Pole of the moon, and now everybody's trying to build a base there.
Well, do you suppose the spacemen, when they're there, will just walk out on a frozen lake with a pickaxe and bring back big chunks of ice, just like here on Earth?
That depends on what form it's in. It might be mixed with soil.
Oh, well,
So-
that's not good.
Now, what is it? One of the probes
What if they have
in
frozen lake?
2020, NASA confirmed the existence of water, molecular water, near this Clavius crater. And this is not at the South Pole. It's in areas that gets complete sunlight, but it's only at concentrations of 412 parts per million. So the speculation is, because they get a strong signal, they know it's there. It could be trapped into tiny bead-like structures in the soil that form out of the high heat created by micrometeoroid impacts. It could be water that's sheltered between lunar soil grains, or it could be from very small asteroid strikes, such as a rubble pile from a more massive parent asteroid.
Wow.
I'd vote for that one.
Mm-hmm.
Well, the rocks in space that have the water are usually comets. It's what gives them
Yes.
the tail. And therefore, if any of those crashed into the moon probably became like a comet for a while, didn't it? It might even look like one of those Saturnian moons that are spouting it up.
If it shook the water loose, you'd get a water plume.
Wow.
But the carbonaceous chondrite asteroids or meteoroids are 22% water. So if one of those landed with a slow enough speed, it could be chunks of it laying around.
Where do you suppose the water comes from? How is it made in stars?
Oh yeah, eventually, yes. It comes, yeah. You can see water flowing out of novas.
Really? So it's not just
And
it's not just oxygen and hydrogen atoms deciding to combine in space.
it combines during the explosion. In the star, there are no atoms. In the star, there are nuclei and electrons, but they're all ionized. It's a plasma. And when the explosion blows up, it moves into a less energetic, cooler, it cools off. And so all of a sudden, the nuclei start attracting atoms or electrons, and it makes atoms. And then atoms run into each other. It's still dense enough, so there's a lot of collisions. But now atoms formed, and as you cool more, molecules form, and that's where the water forms as you get away from the star in these explosions or mass ejections from a planetary nebula formation.
Oh, how interesting. That's interesting.
Somehow chemically, hydrogen and oxygen atoms really love each other, don't they? Thank God. Love to combine.
See, your use of the phrase hydrogen and atoms love each other, that's anthropomorphic
Yeah, that's
attribution
true. Well,
to opposite. Right.
also-
But that's how people understand science. They relate it to
That's
human
well, that's
spirit.
why I'm on board here. It also gives us CO2 and CO1, carbon monoxide, for crying out loud. Those aren't good.
Yeah.
Fascinating stuff. You know what would be a good transition here, Mr. President?
What?
To something falling in on Jupiter.
Oh,
Since we're talking about asteroid impacts, apparently one happened, and you didn't have a lot of details, but we go there, we can see how it affects the big gaseous planets. Certainly those of you, was it Shoemaker-Levy that left a trail of black spots?
yes.
That's the name of the, I guess, what was it, a comet or a large asteroid? I guess it was a
It was
comet.
a comet that broke up,
Okay.
which was on its way to becoming an asteroid. This is a very nice picture of Jupiter. It does not show an impact star or anything like that. It's just a good picture, so I showed it.
Right, but it's still got its red
So
navel.
this is a hit here.
Ah.
This is one of those images that I told you where you take a large number of pictures in a video, and you can see all of a sudden, I think it goes top left to bottom right, but this was done, as you can see from here, in China, And so I don't know if they read top to bottom or left, right to left. So I don't know which way to go here, but we'll assume they start here and you go along here, and then all of a sudden you see this white spot.
Ah,
There it's really
not a
white.
black one, not a black spot
No.
this time.
Now, this is the energy release. Later, it will form a scar. That's what Shoemaker-Levy did. And
Oh,
the
that's what-
Shoemaker-Levy hit when the Jupiter was on the other side of Jupiter. So we didn't actually see the hit. Then as the planet rotated, we saw the dark
Scars.
scar come around.
But it broke up coming in and became a whole line of littler rocks.
Yeah, and you know why it broke up?
Now, if it were a star that it was going into, it would immediately be subsumed and vaporized. But what happens inside a big gas ball? Does the rock just go to the bottom, go to the sink all the way to the center of the planet, or is it vaporized?
The Shoemaker-Levy broke up because of tidal forces from Jupiter. That is, it came within the Roche limit, where the object wasn't strong enough to hold itself together in the various pulls.
That's
So,
not what I'm talking about. I'm talking about.
I know, but I'm leading into it.
Oh, I'm sorry. Go ahead.
So if the comet Shoemaker-Levy would have been a gaseous body, and it came in such as just a clump of gas, it would have come apart sooner because there's less tensile strength in a gaseous body.
Okay. But if a rock goes into a gas planet, any of those four out there, does it stay a rock and just sink? Do they know?
If
one
it
of those
has enough
things.
tensile strength, if it's, say, an iron meteorite.
Until it gets to a temperature inside where it melts.
Yeah.
Aha. Just the collision alone would provide that temperature, probably.
This is a
Yes.
bigger impact than I thought it was.
Well, heck, it's probably the size of the Earth, wouldn't you imagine?
Probably bigger.
That splotch,
Or it's moving very fast.
but nobody saw it go in.
Oh,
Did
yeah, this is it.
Oh, is there a little thing in space next to the big red giant planet? I don't see
Oh,
any.
this little white dot.
I know, but that's after the fact. That's after it crashed, isn't it?
No, it's brighter than the disk. So this is the energy released as it hits.
Right. In other words, we didn't see it go in like we did Shoemaker-Levy, I think.
You didn't see
You
Shoemaker-Levy
didn't
going.
see it before it hit.
Yeah.
That's what you're saying. No, we didn't see it before.
Weren't Shoemaker and Levy monitoring that comet? It got a name before it fragmented and
Right, but it fragmented, and when it impacted Jupiter, it did so on the backside of
It was a
Jupiter.
comet, and we were following the comet.
yeah. So didn't they see it split up? And I guess that part was not seen in the after the fact. Huh? This is fascinating stuff.
Okay.
Supposedly,
Got a sign here that says my internet is unstable. So if I disappear, just carry on.
well, I may too, but doggone it, good stuff. Okay.
We got 4 minutes. Actually,
Yeah,
no,
we got-
more than 4 minutes. 10 minutes. Wrong clock.
You sent out the word potpourri and you included Mercury and some moon stuff and the
Yeah,
heart.
just a list of several things.
Yeah.
This is one that I saw in an ad and I grabbed it because it's looking down on the earth.
We're losing your sound there, Jerry. Jerry, I think you're
And
compute. We can't
around
understand you.
sunset or sunrise. That's normal.
Oh, there you are. You're not moving, but I
Okay.
heard.
It's normal that we don't understand you.
Normally it's me that have, what are we looking at here? Can you tell us
Yeah.
that? We lost him. Jer.
This is looking down on the earth at the space station.
Oh. Okay.
Okay. This is a crepuscular rays from the top.
What does that mean?
Well, we showed a picture of at sunset of white light rays in the sky called crepuscular rays. You recall that a few months ago?
That's not the lightning that goes up from the clouds?
No, this is not lightning.
Right.
This is the shadow of the cloud here. If we were down on the earth, these would look like crepuscular rays.
Oh, yeah, I think I do remember that.
Okay. And this is a space station view of it. Wonder what
Well,
part.
I think, Ron, what he's saying is that light is coming from the side to the right. It's creating these shadows that are streaks. And those are the crepuscular rays that we are seeing from above.
I think we lost Jerry. So we may have to take over until I hope you can hear us, Jerry. We don't hear you. But I'm wondering what part of the planet are we above here, other than the rays and the clouds? Is that North America, Asia, Africa? Doesn't matter.
Doesn't matter.
It's Santa Barbara because they're in the fog.
Uh-huh.
So he's gone.
We lost him, but we're on our
There
own.
you go, Tom. Take over.
Fascinating stuff, nevertheless. What are you guys doing with your telescopes? You want to tell us about it, Tom Whittemore?
I have a question for Tom real quick. I know he can answer.
Okay,
Is that okay?
go ahead.
When we were talking about retrograde and prograde,
Mhm.
one of the things I was at the Bakar last week, and I was thinking about the retrograde. I got a question on it, and I was thinking in terms of inferior planets and the planets outside of us. And I mistakenly said, "Oh no, we're not going to get any, retrograde." And I went, "Wait a minute, Mars has a retrograde." And then
Right.
all of a sudden, it occurred to me: do all planets have a retrograde? And some of them we don't notice because they're so far from us.
Right.
Retrograde is an optical illusion.
Sure it is, but
Planet
does it apply to both?
So let Tom answer that. I'm expressly asking him.
Okay.
Right. As Jerry mentioned before he left us,
Vanished.
retrograde motion can be exhibited when cars are passing one another. It just looks like you're going backwards. The degree to which you see this thing exhibited, though, has to do with how close you are to the planet and how fast relative to the other planet you're moving. Mars exhibits the most incredible retrograde motion you'll ever see, where it looks like it's actually going backwards. Of course, it's not. We're all going in the same direction. Okay, we just overtake Mars. That's all.
Okay.
The inferior planets, Mercury and Venus, will also exhibit retrograde motion. Okay, they will exhibit that. The planets that are further and further away from us do go through retrograde motion, but they're so far, for example, like Saturn, even though it does exhibit it, it's not obvious like Mars is. Mars goes through retrograde over the course of about 2 months, month and a half to 2 months. Okay, you can easily see it moving against the background stars, Tim.
That's a great answer. I now realize that my mistake that I made.
So both planets inside the Earth and outside the Earth will exhibit retrograde and prograde. Prograde means they're going in the same direction.
But if we're answering that to people at a star party, I should be saying, look at planets like Jupiter, Saturn, Uranus. You're not going to notice because they're so far away.
That's right. And I was going to mention Iran. What I've been doing lately is I brought out a 92 millimeter triplet. And some of my favorite stuff is now culminating over the meridian, right over the south point, including the last 2 stars in Scorpius, Less South and Shala. Those are the stinger stars. And there's just a host of really beautiful stuff there, including Colander 338, which is a beautiful collection. Some of these things you can see with binoculars, but a 92 millimeter will actually bring out some of the power of these open clusters. I'm really into open clusters. Probably more than most people need to be, but small refractors really bring this stuff out. There is another star that Less South and Shala kind of point to. It's actually not far from Ptolemy's cluster. Okay, it's called G Scorpii. It's a variable star, but in the background, okay, is a globular cluster about 30,000 light years away. So if you show this at a star party, okay, you can tell somebody that the starlight has been coming to you for about 126 years. but the little fuzzy you see in the same field of view, and it's bright, it's about 7th magnitude, is coming to you from 30,000 years ago, a couple of ice ages, if you like. So I love these 2-for-1 sales. I just really, really like the 2-for-1 sales.
What is the number on that glob, Tom? I'll try and find it.
Let's see, NGC 6441, Tim. NGC 6441.
Oh,
if you pull it up and you can share a screen, you can show folks what it looks like.
I think I saw that. I just
it's pretty easy for an 8-inch, Tim. It's a little bit tougher for a 32 millimeter, which is not quite 4-inch.
Gentlemen, we're running out of time. We're down to the wire, but I do have a couple of quick questions. How many of you three that have telescopes are going to be at our Saturday night star party this weekend?
I usually don't come to the Saturday night gigs.
I'll be there.
Tim Crawford will be there. How about you, Bruce?
I won't be there.
Oh, okay. Well, it's good to see you.
How about Bakar, Bruce?
I don't know. I'm recovering from a broken collarbone. So,
oh my, I didn't know that.
So it's not, I don't want to try to mount my telescope on the mount.
Gotcha.
No.
All right. Are any of you going to be out at the shopping center, Camino Real, to see a partial eclipse of the sun later in the month?
Yeah, I'll be there.
Yeah,
I'm sure I'll be there. It's real partial. It's only 7%.
Yeah, I know.
It's an annular. It's an annular too, so it's not full blackout.
And you have the filters on your units?
Oh yeah. Oh sure.
And it starts early in the morning, I think, or at least you set up at 7, and it's about 9 or 10 a.m. that we get the edge. The real people.
The way, Ron, the way I like to show it to the public is to bring a kitchen colander and just project the colander onto a flat, just a wall or something like that. You see the little chips. Hundreds of chips.
So is it in 2 weeks or 3 weeks? Do you have a date?
14 October.
14, it's only
a month and a half away. That's right.
Yeah, 14 October.
Okay, and does anybody know when Chuck McPartlin, our outrageously outreachable guy, is going to be back to do it?
I can't remember the date, but it's going to be maybe sometime next week.
Guess they didn't take their laptop with them, or they could have joined us live from Dublin. But
actually, we've been texting with them quite often. Chuck said to say hello to you guys. Before the show began, I meant to mention it, but he wanted to give a big hello to everybody.
That's nice. Yeah.
I said
loaf of bread at his house for.
He could have joined us with his cell phone. I'm on my cell phone.
Oh, really? Oh, that's interesting.
Yeah.
Well, on Friday night, it was just me and Tom that were there at the meeting. Everybody else was either down or out of the country. And I said, you know what? Chuck McPartlin right now is probably watching because he's an astronomer guy. He's got a damn telescope and it's 1:30 in the morning in Dublin, Ireland. But I'll bet you he's watching us.
We've been bugging him with texts, maybe too much. After all, he did leave to have a vacation.
Yeah,
you're right. Yeah, I hope they're having a good time and have lots of stories to tell. And
me too.
Hope to see you guys all again on the screen. Maybe Chuck will join us by next week on the Astro Hour. How are we going to shut this thing down without Mr. President?
I don't know. We just end it.
I guess we do, but I think he's in control. How are we still on the air here?
Yeah.
He'll end it on the time.
Maybe we can just keep talking until he comes back on and joins us. Bruce went on his side. I guess just clicking on the X will do it, guys. Take care of yourselves. Beautiful wife.